Welcome to podcast 8-6, Segment Formulas. In this lesson we will learn the formula for intersecting chords and its proof, as well as the formula for intersecting sequence. Intersecting chords. It's possible that these chords could meet at the center, and if that did happen, then of course we would just have two diameters and all of these would be radii. Not very interesting at all. Symmetrical, but not really interesting. This is more of what we're concerned with. That if two chords do intersect, then the chord is divided into two pieces. One chord would be A and B, the other chord would be C and D. The formula states that A times B equals C times D. This is what I'm talking about. If you take the number A and the number B, the number C and the number D, and if one of those four are missing, for example D, then how can we find that missing piece? Well, we simply just place numbers into the formula. And it would look something like this, putting the 9.48 and so forth in these spots, and just a little multiplication division will get the answer. There can be a more unique situation, and that is where one of the chords is a diameter and the other chord is perpendicular to that diameter, like this. So, should we have perpendicular? One thing is true, the chord BD is bisected. Therefore, BE and ED are the same. So if these two pieces are the same, that's rather unique. We don't need to know both. If we knew what AE is, in this case, the 4.8, and if we knew EC, then we could find both of these pieces. So with this formula and labeling both of the missing pieces as X, that is, this piece is X as well as this one, two variables unknown but both equal, then we can put the information in the formula like this, getting X squared, and then a little multiplication and a square root, and we'll have the answer. To prove A times B is equal to C times D, we're going to do the following. We're going to first create some triangles, very typical idea, and we're going to draw another one over here this way. And here's what's unique. I've drawn a chord when I create that triangle, creating an angle over here. I'll call it angle 1. I've also drawn this chord, creating an angle down here. I'll call it angle 2. What do we know about angle 1 and angle 2? Is that they are inscribed angles. That is, angle 1, if we follow it down, we'll get to this arc right here. Angle 2, within that, the interior of angle 2, goes to the same arc. Since both of these angles, inscribed angles, utilize the same arc, and that arc again is right here, then these angles must be congruent. So we know angle 1 is congruent to angle 2. We also know that these two triangles have vertical angles here and here. Therefore, the third angle must be congruent, and now we have what's called angle-angle similarity. If the triangles are similar, the sides are proportional. So if we match up the proportional sides, A of the top triangle would relate to D of the bottom triangle, and that would be the same ratio as C of the top triangle to its corresponding part B. And by cross-multiplying this proportion, we get A times B equal to C times D, which is what we were trying to prove. Intersecting sequence. Intersecting sequence would look something like this, and possibly even something like this with a tangent instead of a secant. But they do intersect outside of the circle. When that happens, the following is true. This portion ED times the entire piece EA is the same as this portion EC times the entire piece EB. To say that in another way, the outside piece times the entire segment is the same as this outside segment times the entire one. Or as I've said, the outside times the whole is equal to the outside times the whole. Or you could even abbreviate that OW equals OW, better known as ow, ow. An example of what I mean goes like this. So we know a few of these numbers, like we know ED here, and we know AD, the inside part, not the outside part, and EC, the outside part, and we're looking for CB, the inside part. Now the formula doesn't state the inside part. I said the outside times the whole thing. I gave you the outside and the inside. So we're going to have to add these two together to create the whole segment EA. So the outside portion, 2.5, times the whole thing, add them together to get the entire segment, would equal the outside portion, 2.3, times the whole thing, 2.3, plus the inside, like this. And then it's just down to a little bit of arithmetic and some algebra, and we'll have the answer. The method for proving this is similar, and that's a joke. Similar, yes, using similar triangles. I'm going to create this chord here, creating a triangle this way. I'm going to fill that in with a little bit of color. So let's call this the yellow triangle. But I'm going to create a different triangle by drawing this chord going this way. And that makes a triangle where this is the vertex going down here. And we'll call that the green triangle. Obviously they share some things. And let's talk about what they share. First off, this angle of the triangle is an inscribed angle, and the arc in which it goes with is right here. But then so is this angle. It's an inscribed angle, and it goes with the same arc. Therefore, this angle up here is congruent to this angle down here. That's one pair of congruent angles. The triangles overlap on this angle right here, and that's two angles congruent. The green triangle has these two angles, and the yellow triangle has this one and that. And we call that, once again, angle-angle similarity. And now we can create ratio. So looking at the yellow triangle, I have this side down here called C. It's part of the yellow triangle. C of the yellow triangle would correspond with A, this side right here, of the green triangle, A. And that should be the same as, for the yellow triangle, A plus B, that whole piece, A plus B. And that would correspond for the green triangle, this entire piece, or C plus D, C plus D. And with this proportion, if we cross multiply, we are going to get A times A plus B, like we see here, is equal to C times C plus D, what we see here. This has been podcast 8-6, Segment Formulas. Thank you very much.